would like to start by thanking the organizers for the invitation. It's nice to be again in a conference, in presence at least. And I want to present a very short paper that we made with my collaborators, Luigi Bianchi, and with my former advisor, Luciano Tubaro, well, the title is A Class of Fractional Ornstein-Uhlenbeck Processes, and we will show in a few moments why the title, mixed with the gamma distribution. So the idea is the following: there is a rather old paper by Dick in 1999, where they proposed the following model. You have a sequence of stochastic differential equation, one-dimensional, very easy. So this is exactly an Ornstein-Uhlenbeck model, where alpha k is a sequence of IID random variables which are independent of W. W is fixed, so there is no k here. There's just one Brownian motion, and alpha k is a sequence. The idea, in order to simplify notation and somehow the exposition, is to take two different probability spaces. One is omega for W. The second one is omega bar for the alpha k. So if I fix omega bar, so I have a sequence of numbers here. When I look this as a stochastic process in omega, I have a sequence of Ornstein-Uhlenbeck processes. So in particular, for fixed time, they are Gaussian random variables with given mean and variance, zero mean and variance that you can explicitly compute. And then what you want to see is what happens when I mix. So when I do something like, something like I take the empirical means. So I just take n realization of this process, and I take the mean. Okay, so the theorem proved in 1999 was that if you take alpha k to have this kind of distribution, then the sequence yn converges p bar almost surely. So again, when I think about what happens with omega bar fixed to a Gaussian random variable, and the convergence is not only pointwise, but it is in the sense of processes on the space of continuous trajectories, let's say for any arbitrary interval. Okay? And what is interesting is that now you have diffusion coefficient, which depends on the parameters of the alpha, clearly. But it is no more, it's not anymore related to a differential equation. So this is not a solution of the Ornstein-Uhlenbeck process with the average alpha, for instance. Okay, something completely different. There were a lot of, well, there is some papers in the literature. I list just these four because well, because Cyprian is a friend of mine, if you want, and this was the original one, and then there are some few recent papers where, in general, the idea is to replace W with more complicated processes, like the fractional Brownian motion and so on, and see what happens in that case. It was our idea to start thinking about a different generalization. So instead of taking the exponential here, like in the differential case, I just want to take a more general function, two parameters function. And in particular, in a, let me just go here, I want to take the sigma that is related to this process. And I call this process a fractional Ornstein-Uhlenbeck process because I don't know what else to call it, because G rho is the fractional integration kernel. And so alpha k satisfies this kind of equation. Sorry, xk. Again, the notation are the same. So alpha k is a sequence of IID random variables on the space omega bar, and W is a Brownian motion on the space omega. The setting is just the same. Rho is kernel, and well, in order to solve this equation, you don't have to impose any condition on rho. Well, rho larger than 0. But for what I will need later, I'm not able to go for on rho between 0 and 1, and can only take rho between 1 and 2. Clearly, rho equal 1 is nice because it's a previous example, so I will not use that. And okay, so this equation has a solution which can be given explicitly, and probably you already know this, and everybody in this room. So this is given in terms of the Mittag-Leffler function. Okay, here I forget the k, but you understand what I mean. So for any fixed alpha, let's say alpha number for the moment, I have that the fundamental solution of this problem is just given in this form. And so the solution of my equation can be written as a convolution with respect to this function as alpha k for any k. And again, I insist that this is a random variable with respect to two different probability spaces, and I will just want to study what happens as a random variable in omega and see what we can get if I take the average. And so the average is in my idea in omega bar. Okay. And as you see, this is a special case of this function that I was writing, sorry, here. And maybe later we can discuss a little if there are possibilities of other extensions. So this is the main object that I want to study. And the idea is that, okay, let me come back for a second to the previous slide. Xk is given in this form. If you take the sum of Gaussian random variables, then you know that the sum of Gaussian random variables is a Gaussian random variable with variance, which is given by the sum. Oh, if you want, if you take the sum of the xk, you just take the sum of these functions inside this integral, and then you divide by n. So what do you expect? I expect that when I pass to this function, I take the 1 over n, the sum inside. I hope I can use some sort of low large number. And so the alpha k should converge, will converge under some assumption to the expectation. The expectation in omega bar. And so I take this function here and I put inside this integral. And I try to prove that yn converges to this object. And so two things here, the convergence and, well, is this function well defined? Because for the moment, it's just formally written there. I try to write this as motivation as the expectation of this function. Okay, so the goals of the paper are three, more or less. The first one is the definition of this function. The second one is the convergence. And the last one, which was the one most interesting for me, is what happens if I send t to infinity to this process. Is there a stationary solution of the problem in some sense? Well, there is not a problem really. There is not an equation that is solved at the problem, but I want to see if somehow there is some stationarity of this, I don't know, problem in a generalized sense. Okay, so the first step is what is this function? There are, I don't know, I think that I found in the literature some 1,000 extensions of the Mittag-Leffler functions, but I was not able to find this one, so I have to introduce it by myself. As you see, this function is missing, for instance, with respect to the talks that we have seen before, is missing the k factorial here. which is typical in this kind of, so this was the 3-parameter meta-Cleffer, if I remember correctly, but there should be a k factorial here that we don't have. And since we don't have this, in order that this function to be well defined, I need to check what happens to this ratio. And the numerator grows like k factorial. And in order that these coefficients don't explode, I need that this goes faster than k factorial. So this is the motivation why I need rho larger than 1 here. Okay. And then it's rather standard. You can make a few computations, and I will just skip the proof. And under the assumption that rho is larger than 1, this function is an entire function with radius of convergence plus infinity, and the order is rho minus 1 divided rho minus 1. Okay, so this is just to say that the function that I need is well defined if I choose rho larger than 1. And somehow it seems difficult to extend this for rho less than 1. So this is a first thing that is interesting to underline. So I can work in the regime between the heat equation and the wave equation, but I cannot go beyond. Next step, okay, there is a nice picture here, which is not really important, but just to fill the slide. What is important is the estimate. And as you see, the estimate for large x, and I use the typical notation with minus x because it's what I'm interested in here. And the bound is, well, it's a constant 1 over x plus 1 over x to the power mu, as x goes to infinity and mu is different from 1. From mu equal 1, there is a logarithmic term that comes out, and well, it's not really important. And I will need this at the end in order to see what happens on the asymptotic behavior of the solution. The gamma distribution, okay, is just something that just to remember you, there is this nice formula for the expectation of the powers, so the moments of alpha, which can show you that where the procurement mu n and the power 1 over lambda n comes out in our definition before. And there is a remark here that says that alpha to the power minus 1 over rho belongs to L2 if and only if mu is larger than 1 over 2 rho. And this is, well, something that I will need at the end again, and that is related to the fact that if you remember in the, it was written, but I didn't emphasize it, in the paper by degli, they require that mu should be larger than 1/2. And this is quite consistent with our assumption here. Okay, so again, this is a reminder of the relation between S alpha and the Nita-Gleffer function. And the result that we were expecting. So if I compute explicitly the expectation with respect to the space omega bar of S alpha t, I can just take the expectation inside. Well, I can prove that I can take the expectation inside, and I get exactly the definition that I was suggesting before. So, well, I have this expectation here, and I have this formulation for yn, and what I want to do is, well, I want to apply the low large number, and then send this quantity to the limit, and the limit is just expectation. So if things go in the correct way, what I expect is that the limit of yn converges exactly to this process. And this is the next step. Prove that this holds. Unfortunately, if you want something which is uniform in T, for instance, so if you want convergence in the space of continuous function, you cannot just do this taking the expectation inside or taking the limit inside. Some more care is needed. Okay, so this is the main theorem, and the second goal, that is, I have the convergence almost surely with respect to the product P times P bar. So in the product space, our process converges in C0T to Y. So the sequence Yn converges to Y with respect to the uniform topology. So the sup of the difference goes to 0 almost surely. Almost surely with respect to both variables, omega and omega bar. And well, I will give you a very short idea of the proof because it's quite easy. And I just want to show you that how to work this. So I have a convolution here, Fn star W dot and F star W dot is respectively, sorry, the process is Yn is a convolution, a stochastic convolution of a sum of functions, and Y is a stochastic convolution with respect to this function G mu rho. Okay, so it just this, but this really holds in general. I can just take an integration by parts here, and so this difference, that was the difference I wanted to estimate for any t, can be written in this form. And now there is a constant c such that I can just take the sup in 0t, 0 capital T of W, okay, and I can take the sup of this quantity here. And so the supremum of the difference in 0t is bounded by a constant, which depends on omega, and then I have Fn, the difference of the initial conditions, which in our case is easy because it's 0, and then the difference of the first order derivatives. So in order to prove the theorem, I just need to prove that Fn0 converges to F0, that Fn dot converges pointwise, and then I can apply dominated convergence theorem. Okay, so that Fn dot is bounded. And maybe the only thing that is necessary to give an idea is just the last one. So Fn is given by this sequence of sums, and then I can take the derivative inside because this is a finite sum. And if I take the derivative inside, I see that I can take the derivative of S alpha k, and as this function is a Mittag-Leffler function with time changed to t to the rho, but it's not important. You can do this explicitly, and you have an explicit bound for this. And this explicit bound takes out alpha to the power 1 over rho, and then a quantity which is bound. And m is a constant, which does not depend on alpha, the only important thing. And so you have that since this random variable is integrable in omega bar, P bar almost surely, this quantity is finite. And so you get that you can apply again the law of large numbers, and you have that this convergence holds. And this, sorry, this is a bar here. I forgot in the slide. Both here and here there's a bar. And so there is another constant, which is P bar almost surely such that this holds. And then you put everything together, and you prove that P times P bar almost surely you have the convergence. I will just skip the details of the rest of the proof. Instead, in the last 5 minutes, I want to discuss the asymptotic behavior. So I have this process Yt, which is defined as the integral between 0 and t, and I want to see what, okay, first of all, I already said it. This is a Gaussian process, and 0 means the variance can be computed explicitly. And I want to see what happens if I extend t to plus infinity. Okay, so the Ornstein-Uhlenbeck process converges to a Gaussian random variable. The fractional Ornstein-Uhlenbeck process converges in our assumption for P bar almost surely, let's say. And I want to see what happens to the empirical means, so to this average. And the theorem is written here. So if you have mu larger than 1/2 rho, which is the condition that I was saying before, and lambda positive, then there exists a Gaussian random variable eta that I can completely describe. So I can say the expectation is 0, and I can completely say the variance, such that yt converges in distribution to eta. And the idea of the proof is typical, or at least for in my knowledge. So instead of looking at what happens when you send t2 plus infinity, you change time, you make a new sequence of processes where initial time minus s, final time, let's say 0. And so the law or the integral between minus s and 0 is the same as the law of the function between 0 and s. And instead of looking at what happens to this sequence when you send t2 plus infinity, it's sufficient to see what happens to this sequence when you send minus s to minus infinity. Okay. And well, this is easier because you can make explicitly computation in this case. And for instance, you can prove that this sequence is a Cauchy sequence in this space. Notice that there is no more omega bar because now our process is just in a random variable in omega. And you can prove that there is a Cauchy-like condition that you can just prove by taking the estimate on G mu rho. And then this implies the convergence. Okay, as you send the initial time to minus infinity. So almost done. And now that I have a stationary process, okay, I want to see that also in this case, I have the convergence of the empirical means. And so the idea is, let me take the extension of the xk, so ck are the same as the xk, but now the integral is from minus infinity to t. And I want to see that the empirical means of these random variables converge to the process that I've seen before. And okay, this is exactly the result in this theorem describes this function. This object is again a Gaussian random variable with mean 0, and the expectation can be explicitly computed. And in particular, the computation shows that, okay, S alpha is bounded by 1/alpha to the 1/rho. And then I will need this. This is again the same condition that I was saying before. The relation between this and the other. This is what we were saying before about the limit. So the xk, so they should define the empirical means. Then this is the limit. And the last theorem just says that the empirical means, defined this way, converge in L2 omega p to the process eta p bar Moschule. And this is the last result. And I have just 1 second to extend it. So this is a convergence for fixed t, and I have just 1 minute to extend this to the fact that the convergence actually holds in the space of trajectories. Okay? Thank you for your attention.
Thank you very much. Okay, time for questions.
Thank you for talk, really interesting. And in my view, you did not mention dependence. I mean, probably, at least in this scheme, you can convergence not only to the Gaussian limit, but to the fractional Brownian motion, because of here is dependence meant the so-called long-range dependence, and you can proceed basically.
Yeah.
I mean, am I right? I'm probably right, but
yes, you are probably right. There are a couple of things that I didn't say because I don't know how to say it. So this is just a first attempt. We choose a very special case of a convolution function And we make all the computation explicit because beta-Leffler function is well known, and so we know how to treat. There are also other possible extensions. The first one, which is for me the most interesting, but I'm not able to think of how to obtain it, is suppose that you want to fix the limit process y. So for instance, suppose that you want to construct the fractional Brownian motion as the empirical mean of some other kind of processes. So is it possible to choose the target function? So let me see if I have a slide at the beginning. Is it possible to choose the target function here in order that you can construct this sequence that converges there? Okay. And yeah, and then we didn't study the properties of Lorentz dependence of y, for instance. There are other extension that was possible. But in my opinion, it is interesting to see if anybody has an idea how to go back from here to the other process. That would be very important.
And again, this is very similar to what Bardov-Timsen called superposition of Ornstein-Uhlenbeck processes, which is not only with Gaussian, but also with any Levy process. And the question is why you have a gamma distribution. You can use any positive distribution, inverse Gaussian, you can use.
Yeah, of course.
That's a kind of, there is some view from this point of view. But anyway, thank you.
Okay, any further questions? Yeah.
So again, thank you very much. So I wanted to ask a bit what was the motivation for the original problem? And also you have a single Brownian motion for the whole set of equations and not independent or correlated Brownian motions. So
okay, so
I've seen similar problems in finance, so I was intrigued.
So I think that I start from the second part. It is, in my opinion, possible to use also a sequence of independent Brownian motions, in which case you have a situation which is similar, because when you take this sum, you have a sequence for fixed omega bar, you have a sum of independent Gaussian random variables instead of having the sum of a Gaussian process, let me say in this way, which is okay. So there are maybe some things that should be checked, but I don't think that this extension is it's much difficult. The other part of the question was something about if we can do some other scaling here. Motivation was just curiosity, nothing else. It's just I don't have any model in mind. It's just my curiosity to see what happens in this case.
But I think it's important for econometrics. Definitely in econometrics there are such models.
Yeah.
You reference Bardov-Timsen and Shepard.
Yeah, I remember.
And basically they did a lot of motivation.
Okay.
Actually, I've got related questions. You show us original Ornstein-Uhlenbeck process.
The original one?
Yeah, at the beginning.
Thinking. I don't know if I'm going up or down.
Yes, exactly.
Oh, okay, too much. Sorry.
Well, for this process, it seems easy to justify why alpha k is gamma distributed. And then, of course, we need to know the rate at which we have relaxation towards Boltzmann distribution with quadratic potential. So clearly alpha k is explain heterogeneity, and that's related to your questions, Nikolai. But now in your case, when we do the same thing for alpha, when alpha distributed, let's say like beta distribution, it's clear. Yes, but now it's an infinite domain. What kind of motivation, or again, what your picture have in mind? Because here it's clear, but when alpha distributed according to gamma distribution.
Since my idea is that, okay, if you take this equation in integral form, we have x is just minus alpha 1 star x plus w. And my idea was, okay, instead of having 1 star x, I want to put g rho star x here. Okay. And I didn't see any reason to change the alpha. But as I was saying before, this paper is motivated just by my curiosity to see what happens and if there are, okay, the long-term goal is, can we get the process that we want solving this kind of, proceeding in this way, okay? But I didn't find any reason to change the alpha. I thought about this, but there are no, it's in my, since I don't know about applications, there are no more natural sequences. If you want to suggest some, I will be happy to see what happens. But it was just the idea, for instance, to take alpha to be a beta distribution can be a good idea because inverse Gaussian, okay.
Yeah.
Something that is positive and
Finite domain.
yeah. Okay.
Okay. Thanks. It's a clear explanation. Curiosity-driven research. I like that.
It's in, but it's on the archive and it will be published. I hope so. Okay.
Okay. Thank you again. So it's time for lunch, and let me remind you that we will start at 2 p.m.